And then what we get when we have this used nuclear fuel, we have all kinds of uranium-6+ alteration phases, such as Shepite, which is hydrated UO3, or if you have some calcium silicon in the system, you get layered structure, such as boltwoodite. And these are potential hosts for elements such as, so transuranium elements such as neptunium. And so one of the things that we do is like, what is the thermodynamics of neptunium incorporation? What is the mechanism of neptunium incorporation in all these essentially corroded phases that we might get once the container is leaked away, corroded away, once the uranium dioxide is oxidized. Essentially, what we will also have from the corroding containers is a lot of iron oxide, such as goethite and hematite, and we look at the adsorption mechanism. Actinides are nasty for two reasons. First of all, you don't want to have it in the lab because you have to fill out a lot of forms before you can actually work with them experimentally. So we can do uranium in the lab. We cannot do neptunium, and especially we cannot do plutonium. We can put them in a computer. We're allowed to do that. However, they have their own difficulties. There's a lot of relativistic processes or effects going on. And the 5f orbitals of the actinides are strongly localized. And depending on what property we're looking at, for example, if we're looking at solid solutions and look at the excess energy, the results fly all over the place depending on what U parameter we choose, and we have a really hard time benchmarking this. Let me just show you a few other applications that might go on surfaces. If we use an AFM, which is even simpler than the STM, essentially we just scan over the surface and touch it. And we can do this sensitive enough that we can see monoatomic step here. So this is barite, barium sulfate. And as you might know, most of the crystals that grow from imperfections, which in this case would here be a screw dislocation. And then starting from this screw dislocation here, would be a spiral growth. And so we would see these spirals growing. On top of that, if we are highly enough supersaturated, we would get these two-dimensional nucleation. And what you see as you jump up one barium sulfate layer or half a unit cell, the orientation of these islands changes. So the atomic picture or the modeling picture of this would look like this. Kinetic bottleneck is starting a new row. Keeping a row growing once it's there is really easy because it's really easy to add a sulfate here. If you start a new row, crystal growth is always a competing effect between hydration, which wants to dissolve it, and adsorption, which wants to grow it. If you have it here, there is not much coordination towards the crystal. It's essentially energetically unfavorable to start a new row. How do we do this? Essentially, we combine empirical force field is good enough for this process because it's an ionic crystal. But then we have to essentially throw molecules on the surface. We have to get hydration energies depending on the site where we adsorb it very precisely. And then what we see is that it starts adding to this, and only occasionally it starts growing a row in the other direction, which is energetically less favorable, which explains that it grows about 10 times faster in this direction. And in the other direction, on the next layer up, it would grow in the other direction for symmetry reasons. We are also involved essentially in calcite and phosphate bone growth. This would be, if we just relied on the computational approach, it would be too demanding to find polypeptide sequences that actually work well in growing, such as your bone apatite. And so we use the experimentalists that create these fast genomes that have millions of different peptide sequences. And essentially, they put it in a solution, then they wash out these, do it again, and then they find a sequence that way that works well. And essentially, we can then calculate how they adsorb to calcite or phosphate surfaces. And we've heard a lot about molecular dynamics approaches this morning. And I just want you to see two examples on how these polypeptides adsorb to, in this case, a calcite surface. Here you have sort of the carboxylic group adsorbing to these steps, whereas this one comes on and off and on and off and on and off. So it's a very dynamic process in water. And essentially, we can also simulate more complex surface. This is the second to last slide. We also do a lot of solid solution work, not at the high level that Renata described it. Essentially, we do the quantum mechanics first and then do Monte Carlo simulations to find the delta H, delta G, and delta S of mixing. What is the ordering exsolution mechanism in a number of geochemical applications? And sort of one slide that I wanted to show. There's a lot of choices that we need to make on, and only some of which I posted here, which is on the dimensionality of the system, which is on the approach, which is on the basis that depending on the properties that we're interested in, a lot of people use DFT plane wave approaches for magnetic interactions, which are typically underestimated if you do this. Is it better to use localized orbitals rather than plane waves? Something like the Hubbard-U parameter is very sensitive to excess energies in solid solutions. Relativistic effects are often only included in how the pseudopotentials are constructed. And this is one thing that I would like to caution people. The bigger computer you have, the more atoms you throw in there, and the more you, or the less you understand the physics of the system. There are a lot of people who do MD calculations with millions of atoms, and they have no clue anymore what is going on in things like interfaces. So we need well-trained scientists and not just big computers that design the best system or the best small-scale system that explains large-scale applications. That is something I talked about already. For example, with too many atoms, you might lose a lot of information on the physics of the system. We use a lot of different approaches depending on it's a bit different from Well, once you use high pressure, often you're forced to use a periodic approach, but it's not necessarily always the best, especially when you have charged particles, which is usually not easily handled in a periodic approach. Dane?
I just wanted to keep my comment on, because you have used a lot of the ab initio approaches and then also a lot of potential approaches, it seems like at least from this meeting, maybe the minerals community, well, maybe I shouldn't even say that, but there's a lot of ab initio work at least. But certainly there's a lot that can be done with potentials. There's a price you pay on accuracy. You know, Renata showed some beautiful work of how hard you have to work to get even really decent accuracy. You still have LDA, VGA issues. So I always sort of am afraid of potentials when you're dealing with milli-electron volt kind of changes, potentially altering phase boundaries and things like that. But do you think that there's a bigger role for them maybe than they're playing, or some opportunities there that we're not taking advantage of in this community? Maybe other people can comment to that. Certainly they're used. I don't mean to imply they're not, but it's a subtle.
I mean, definitely you have to be careful as you go back and forth. I have to be careful if a lot of potentials are developed for bulk minerals and then I go into surfaces and I have no idea, unless I test them again and again and again, if I can do a small scale model of the surface with a quantum mechanical approach. Then I add water, then I don't know if the potentials work. I don't really know. Sometimes you may even get for high pressure applications. Give it a try for an afternoon and see if you come up with a quick and dirty idea of what might be going on, but you may have to go back to a quantum mechanical approach.
If I can comment on that, another approach rather than completely computational would be to involve experiments and work with them to benchmark these potentials as well, not just theory. So I think that's where the merit comes in, much more closely to work than many other places like high pressure work.
One last quick question.
Would you classify this work as mineral physics or not? I personally would say it is mineral physics, but traditional thinking was that mineral physics is only high pressure.
No, there is a lot of mineral.
This is a question also to Don.
There's a lot of.
Would you include such research in Compress?
Absolutely.
No, there is a lot of mineral physics also, even if you don't have pressure. There is a lot of, as more as you go to actually surface, reaction mechanism and stuff, it's almost mineral chemistry. However, then, it comes if you go that the mineral chemistry is actually also influenced by the mineral physics again, by really figuring out what the specifics of, for example, actinides are. What physical model do you need to apply to get incorporation mechanisms, adsorption mechanisms, right? Why do you have, you really need to understand the physics to find out why actinides can, for example, form minerals that have peroxyl group inside or form peroxyl on a surface. If you don't understand the physics of the system, you would not understand why this chemistry is going on.